Well, it's the third leg. I might say it's the first leg of the three-legged stool of the curriculum. We do really well with the theory leg of the physics curriculum in undergrad. We have lots of theory courses. We have maybe a computational leg thrown in there somewhere, and we hope we have a big, strong experimental leg that supports the curriculum. And these are the courses where students get hands-on skills. These are the skills that employers like to see. Okay? These are the skills that are good for virtually every student, whether you're going to go to graduate school and have a research career, or if you're going right straight into industry right after you graduate. And so it's important that we see the difference between undergraduate research and what happens in a Buffy lab. They are not in opposition to each other. They're complementary. Undergraduate research is not a substitute for a Buffy lab, and a Buffy lab is not a substitute for undergraduate research. Okay? I always worry when I say how important Buffy labs are that people are going to walk away and the only message they're going to take away is that you shouldn't do undergraduate research. And if I hear anybody say that about my talk, I'll be very unhappy. Okay? Undergraduate research is important, but it doesn't do everything. It's very narrowly focused. A Buffy lab should be broader and should handle bigger concepts, a wider variety of skills. Okay? What's typically offered in an undergraduate physics curriculum in terms of Buffy labs? Electronics labs. By far the most common Buffy lab offered. After that, we see a modern physics lab. That's usually a sophomore year kind of a lab. And then maybe an advanced lab. And there's lots of different variations of what an advanced lab is. Optics, of course, in this crowd. There ought to be an optics course, and it ought to have a lab. Okay? What we're learning is that there might be an optics course in a lot of curriculum, but it might not have a lab, which should make the hair stand up on the back of your neck. Okay? There should not be an optics course without a lab. But it happens. Okay? So what do we know about Buffy labs around the country? So Gabe Spaulding, some of you know Gabe, is undertaking a massive effort on his own to survey all 750 departments in the U.S. that offer an undergraduate physics degree. Okay? What's scary is that number has actually been dropping over the last few years. It used to be 752 2 years ago. Okay? That worries me. But what he's learned, surveying 462 of these, and looking at the number of Buffy lab offerings, not counting electronics, okay, is we have mostly everything's 2 or less. Okay? It's not very many courses beyond the first year that have a lab. We have a lot more than 2 theory courses beyond the first year of instruction. Okay? This one is particularly worrisome. Okay? And your first thought is what my first thought would be. Oh, well, that's all the schools that have very, very low resources. There's 2 faculty members and they have absolutely no support from their administration. No! There are some very large, well-known schools in the 0 category. Okay? So this is not just a financial problem. Right? What do we know? This won't surprise you. Labs either come by themselves or they come with a course. No surprise. Okay? But the format and the goals of the courses lie on a spectrum. They lie on a spectrum from courses that focus on the physical phenomena that students are supposed to be learning to courses that focus on the skills that the faculty want the students to learn, the hands-on skills. Mostly, we're trying to be somewhere within that range. Okay? And the style of courses, I like to use these names, tend to range similarly with the focus. The black box lab is the lab where there is one apparatus for the students to use. Okay? The faculty member has to spend a few hours to set it up so that it's working. And the students will come in and they'll be told, there are 20 knobs here. Touch these 3, not the others, because I don't want to have to reset it all up again. Okay? You do these things with the knobs. You get your data. You analyze it. You try to understand what was going on. That's a black box lab. On the other extreme is the empty table lab, where the students walk into an empty table and they're told, this is what you're going to do. Here's some equipment. Go. Right? This takes a lot less time. This takes more time. what you get out of it is different, right? And we see the whole gamut of styles of labs, right? What do we know about the challenges that face people trying to teach these Buffy labs? The first two, no one's going to be surprised about, right? The knowledge and departmental priorities challenges are less obvious. Departmental priorities are simple. If you have a department of 6 faculty and 3 of them are astronomers, you're probably going to have a lot of astronomy in your department. And you might not have a lot of nuclear physics, right? So you might not have a Buffy lab in nuclear physics because of that. The knowledge challenge comes from the fact that if you are teaching an advanced lab course that hits on a variety of topics, nuclear physics, condensed matter physics, optics, and you got a PhD like I did, you get trained in one area, not all those areas. Okay? And so you have a knowledge gap for some of those topics. And so it's going to be hard to teach those courses. So what resources do we have? Okay? It's called Alpha. Alpha just celebrated its 10th anniversary of existence. We didn't have a party, though, which was disappointing. And it was formed simply to attack these challenges that we see, particularly the knowledge gap. And the idea was that if Alpha can impact a small number of faculty, we can impact a larger number of students, because only a couple faculty teach these Buffy courses in each department. Okay? So if we can help a couple faculty members, we're going to help a lot of students. What has Alpha done? We've offered a number of conferences. There's one coming up in July. The next one, highly anticipated. There's the Laboratory Immersions Program. And I'm only going to touch on it because tomorrow Eric Black is going to give us a much more in-depth discussion of the Immersions Program. Alpha has helped partner with companies to reduce the cost of equipment for instructional labs. We'll talk about that. And advocates, the Alpha program advocates for this aspect of the curriculum. Okay? So quickly, the Immersions Program, again, we're trying to go after the knowledge gap for faculty. So if you want to add a new experiment to your curriculum, the best way to do that is to go do the experiment under the guidance of somebody who knows it. And so in the Immersion Program, students or faculty go for 2 to 3 days with maybe 2 or 3 other faculty and work on an experiment themselves, just like a student would, and learn it well enough to teach it themselves. This program has been going on since 2010, and it is quite successful. I'm only going to talk about one little bit of information about how successful it is, and that's the number of students we know have been impacted and the distribution. You can see that through the 2015 immersions, the distribution is not big numbers. At each school, mostly it's 12 or less students that have been impacted, which is not surprising given the number of students in an upper-level physics class. Okay? But the aggregate is a big number. A big number when you compare to actually how many physics degrees get awarded each year. Okay? So the Immersions Program has, and this is a low-ball estimate of what we've impacted. So the Immersions Program has been very effective in terms of getting new experiments into new schools. Other support. There's a lab wiki where people who've gone to an immersion can keep in touch with the other faculty who are at the immersion and with the mentor. And something new, just this last year, and the person whose hands are shown in this picture is in this room. So try to figure that out. Okay? Just last year, we had a pilot project. Duncan Carlsmith at the University of Wisconsin-Madison went around and helped videotape 4 of these immersion experiments with mentors describing the experiment, walking you through different steps of the experiment. These are videos. They're not 5-minute YouTube videos. These are 45-minute videos. You have to be committed if you're going to watch the whole thing. But that's the whole idea, is that if you go into an immersion and you don't remember all the details of how you might prepare a fiber, okay, you can watch the video and be reminded. Okay? So this is another way we're trying to support. We're going to see how effective these videos of the immersions are. Another way we try to support faculty is to reduce the cost barrier. That challenge is significant. And some members of Alpha went to a company called Excelitas and convinced Excelitas to produce a single-photon counting module for about half the cost that it would normally be, explicitly for educational use. And you'll see why this is a useful device in a couple talks in a few minutes. Okay? Kiko Galvez and Brett will be mentioning experiments that need detectors like these. And this has been very successful. Over 100 institutions have made use of that. Briefly, I want to talk about how Alpha has partnered with another organization, the Jonathan F. Reichert Foundation, which is a nonprofit trying to financially support the advanced labs in physics. They offer grants to implement immersion experiments. And the Minors program, which is helping faculty go to conferences looking for ideas that can be turned into new advanced lab experiments. Okay, so they financially support faculty to go out and try to develop new experiments. How many of you have seen this picture before? Anybody? Few people. All right, good. This is a food truck for the physics mind. It's something TeachSpin, which is a company, this gets complicated, that's owned by the nonprofit foundation, the Reichert Foundation. This is a trailer on a truck. It's just as big as it looks. It's full of 22 different advanced lab experiments. And it can be hauled around and parked in front of a school. So students can do experiments that they don't have access to. Okay? It's meant as a way to bring experiments to schools. So it can come to a school and park there for a couple days. And there's a mentor on board who knows the experiments. So a faculty member doesn't have to know them themselves. Okay? It's another resource. Finally, the American Association of Physics Teachers has recently put together this document, recommendations for the undergraduate lab curriculum. And it's very useful, particularly if you're trying to convince administrators to pay a little bit more money to develop a lab curriculum at your school. Okay? It's giving you a reason why these labs are important, and you can point to it. What's coming up for Alpha? More immersions, more conferences. Alpha is going to be continuing to work to push the federal government, our elected officials, to support laboratory curriculum nationwide, which has not been happening. The food truck we hope to actually incorporate into the immersions program. So when instead of having people have to go someplace to attend an Alpha immersion to learn a new experiment, it's possible that the truck can show up nearby. And that will be a much more convenient way of doing an immersion. And finally, Alpha wants to get even closer in terms of partnerships with industry. So I'll finish with just thanking a number of people who've helped, particularly with creating the Alpha Immersions program over the years, and the NSF for the support of the Immersions program. And I'll leave with an advertisement for the conference next summer. Thank you. On time and under budget.
Very well done. Thank you.
All right. Any questions? All right. Thank you.
And I'm a graduate of that program. In fact, I remember taking that in your office shortly after you arrived. He's going to talk to us about research and education in optics, photonics at UNM and advances in laser cooling of solids, which he's been working on.
Try hitting the Windows button and P well, at the same time. There you go.
Yep. Getting there.
Sorry.
Nope.
Should we try a different... These have to do.
Oh, this worked earlier. Something has changed. All right. Well, no, I don't know why I don't have my. That has to do with this? No.
Maybe close the slideshow and reopen it.
There you go. You got a cursor.
Well,
If I find the cursor,
you-
I know, but
Oh, it's not on here. If you go down, maybe you have. Should I get the screen?
maybe it has to. There you go.
Where's the
No, it's.
Andrew?
I think you have to slide the whole PowerPoint tab like off the screen to the side. That sounds really
Maybe we
Try
could
to grab that.
Well, that's why I don't have any.
Oh, there's no cursor on
There's
it.
no cursor in here.
You want to go down?
Oh.
Almost there.
Okay. All right. Sorry about that. Well, thank you. Good afternoon. Happy New Year. And again, I thank the organizers, particularly Jason, Masood, and Paul, for the invite. It's great to be back here. Just the weather in Albuquerque was just 65 degrees, so it's good to be a little bit warmer here. Anyway, so upon request, my talk is in two parts. First, I'll talk about the research and education at University of New Mexico, our Optical Science and Engineering degree program. And then in the second half, hopefully, time permitting, I'll talk about the advances in laser cooling of solids, which is what we do in my laboratory. Anyway, so Optical Science and Engineering degree program, the OSE program, is actually nearly 35 years old. It was established in 1983 by when I think Ken Jungling and Mullen and Scully at the time. They were in the physics department there. They started it. And then it quickly matured into a multidisciplinary program right now that houses between or administered by these two departments, physics and astronomy and ECE. And again, it's the OSE program, by its nature, it's a purely educational degree program. So it sits, and again, it's quite, we have, well, this number varies, and also it's different from what's in my abstract. But anyway, this fluctuates, but we have more than 30 faculty, actually, in the optics program. Currently, 65 PhD and MS students enrolled. And, for example, we have more than 35 PhDs in the last 6 years that have graduated. And quite a substantial amount of federal grant money that the affiliated faculty get every year. And now the program, again, I show the multidisciplinary nature of this program by my Venn diagram here. It sits between the physics program, the physics and astronomy department, and ECE. Was almost half and half the faculty are distributed between these two. We have also faculty from the other departments, especially more recently, for example, chemical nuclear engineering, chemistry, and also math. And also we have close affiliation with the research centers. And in particular, I should talk about Center for High Technology Materials, which almost, again, half of the faculty, their laboratory, their offices are in Center for High Technology Materials, particularly most of those that are in the ECE department. And also we have very close affiliation with the Center for Quantum Information and Control, CQIC, that is in the physics department. Here is actually just a picture of our affiliated faculty. I'm sure many of you, especially the faculty, recognize many of these faces. They're very distinguished, world-renowned researchers among this bunch. We also have, of course, recently hired many new and promising new faculty and trying to reduce our average age. These group are in the physics department, including myself, and the guys down here, they're all in the ECE. And as I said, we have also a few faculty that are affiliated from the other departments. And as these little C's indicate here, all of these fellow mostly in the ECE department and a few in the physics, their labs and offices are in Center for High Technology Materials. And again, CHTM is a Category 3 Research Excellence Center at UNM. It's been around for many, many years. It's off campus, 60,000 square foot clean room, laboratories, and classrooms, offices, and state-of-the-art facilities for material growth, fabrication, and optical fibers. Of course, they have, known for example, working on quantum dot lasers, nanolithography, superlattice detectors, and semiconductor lasers. And also we, of course, have a fiber draw tower in there. I'm also, by the way, Arash Mafi, who used to be a postdoc here at OSE Optical Sciences Center, is the interim director, and just a month ago was elected or selected as the permanent director of CHTM. So I'm also very happy to announce that finally, after many, many years that I've been there, we have now the go-ahead, and actually the construction has begun for a new physics building, a physics and astronomy building. This is the artist rendition of that, and of course this is designed to have state-of-the-art laboratories for optics and photonics, both educational and research. So the OSE degree programs, again, we have both MS concentrations and PhD concentrations. There are 3 master's concentrations: optical science, photonics, and imaging science. This is rather new. We have added mostly sort of concerns with biophotonics. The PhD concentrations, again, the population of students are in these 2: optical science, which is more fundamental science, and photonics is rather more device-oriented and engineering. And And then we have also imaging science, and most recently we have added a track in quantum optics. Again, the current graduate student enrollment right now is 65, mostly PhDs, and most of the master's students are the ones that along the way also get a PhD. And the degrees awarded, on the average, 6 to 7 PhDs and 13 to 15 master's degrees in the program. And we have graduated outstanding students, PhDs, that are holding prominent positions in academia, national labs, industry, 2 examples of them. Of course, your own Jason Jones and Chad Hoyt, where are you? There you go. Yeah, 2 of our PhDs that are in the audience that we are proud of. We have very active OSE student chapters, optics student chapter, SPIE, OSA, and IEEE, in addition to graduate student, the Graduate Physics Student Association. Anyway, again, I was the chair many years ago, then I was asked to chair the program last year. So one of my initiatives that I'm pushing for right now to have this Institute for Photonics and Quantum Technologies, or IPAC, which is essentially a bigger umbrella that would have the OSE program and also would have a separate optoelectronics track that is in ECE. And also we have a BS concentrations in physics that would sort of encompass all of these programs and have more synergistic relationship between also the center of excellences that we have, particularly with CQUIC. So this is being considered right now at UNM, and like any new initiative in the time of shrinking resources creates panic and freaks people out, but hopefully that would go through. You'll find out. Again, the UNM is, or I must say, New Mexico is a unique position in terms of for research, is that, and it's because of the proximity to these national labs that we have, namely Los Alamos, Sandia National Lab, and Air Force Research Lab, in addition to Center for Integrated Nanotechnology facilities that has been really helpful. And of course, in addition to our picturesque and landscape, and of course our world famous balloon fiesta, I'm just anyway. So we also, New Mexico is one of the probably handful of states that have their own optics cluster in the industry clusters, and we have 96 photonics related firms in New Mexico, and it is, after all, one of the 4 state priorities, photonics. So these proximity to national labs, I want to again re-emphasize, has been immensely helpful and productive in advancing our research. And many of also our students end up working in these national labs, our graduates. So there's very diverse research activities in optics and photonics. I wish I had time to go through more details and to highlight these things. All I have to do is just list them here, and as you can see, it spans many research areas from very fundamental to applied, ranging from biomedical optics, nanophotonics, microscopy, photovoltaics, lasers, and so forth, and also quantum optics and quantum information. But again, I don't have enough time, so I'm only going to focus on one of them that I know much about, and this is my own work, which is laser cooling in solids. So I just tell you a little bit about that and advances we have made. With that, again, here's my next part of the talk, advances in laser cooling of solids. And so what is anti-Stokes fluorescence cooling? Like any other laser cooling, essentially you absorb light at certain wavelength or photon energy, and then you emit it at higher, basically higher energy. And this actually goes back 1929, Peter Pringsheim, way before even lasers were invented. And essentially, if you consider 2-manifold system where these 2 manifolds, of course, quickly equilibrate with phonons, and these two electronic transitions here. And if you, by reciprocity, you have an absorption curve here, and then you have also the fluorescence. The fluorescence is Stokes shifted, is the red one, and the absorption is the blue one. And this is the mean fluorescence wavelength. Notice there's something interesting in this tail here, which we call cooling tail. That means if I do an excitation here, which is essentially shown by this arrow here, if I excite the system below its mean fluorescence wavelength, and once it equilibrates and fluorescence comes down at mean fluorescence wavelength, the mean energy of the photons that are exiting the system are higher than you put it in there, and then that means the system has, you are removing phonons, right? So you're cooling the system. Of course, this was controversial, and the efficiency is given by this, essentially the photon energy difference between what you put in there. And of course, it was controversial initially. People thought it violates the second law, and thanks to Landau, it was put the rest that the fact that he assigned entropy to light and say that the fluorescence is random and carries entropy, and so the second law was safe. Of course, what we have in mind here is cooling solids. And with solids, of course, you have phonons in the absence of any translational energy. And so it's the same concept. There's nothing new here. Except that if this formula, this simple cooling efficiency was all you had, then anything would have cooled, right, many years ago. But the problem is that there is a photon or conversion yield. That means not everything that not every excitation, every atom that gets excited here gives a photon, a fluorescence photon. For example, you have non-radiative decays here, right? And in that case, this fluorescence yield, we call it, is there is a product of two efficiencies. One we call external quantum efficiency, which has to do with ratio of non-radiative to radiative. And also notice it has this eta E, which means the escape efficiency. Not only it has to fluoresce, but the fluorescence has to get out of the system, not get reabsorbed. On the other hand, there are some bad actors that get in there, like transition metals that cause heat. They absorb light and get heat, generate heat, and they're very broadband absorption. And that one we call absorption efficiency, given by the ratio of absorption, background absorption to this resonant absorption. And that's why it took actually 65 years, because it's very stringent requirement to have this product of these two have to be more than 98%. And that's why it took 65 years for first to be observed by my colleague Richard Epstein at Los Alamos in 1995, and they cooled by 0.3 degrees a ytterbium-doped Z-bland glass, right? And that was about the time that I got into this game, and in collaboration with Richard. And actually, Chad Hoyt, sitting back there, was my first student working on this project. And we cooled the first thulium dope and published in PRL, which is highly cited. But anyway, our goal was really to cool these things to very low temperatures. First, to beat Peltier limit, which is around 160 Kelvin or so. Because beyond that, cooling needs cryogens and mechanical cryocoolers. So if you could make a laser cooler to go to these temperatures beyond that, that means you have a solid-state cryocooler, an all-solid-state cryocooler. So our goal was to first go below Peltier limit, then go to cryogenic, NIST cryogenic 93 Kelvin, and liquid nitrogen, hopefully, of course, improve the efficiency, and also really make a device, cool a load with that. Can we do it? And that was really challenging. I'll tell you about it and then, of course, we wanted to cool a semiconductor directly. This remains to be our holy grail. We collaborated a lot with Rolf. Is Rolf here? All right. Yeah, he did a lot of fantastic work on theoretical work on that. We still haven't cooled a semiconductor. And also using this to make radiation balanced lasers, meaning that lasers that don't generate heat. And I'll tell you a little bit about that. So how can we get colder and colder temperatures? If you look at that cooling efficiency, if I write it in terms of its constituents, the problem is that as the temperature drops, mean fluorescence wavelength redshifts, this resonant absorption drops because you basically empty the top of the ground state here. And so your absorption drops, and at some point this cooling efficiency goes to 0. or reverses, becomes heating. So that's a minimum temperature you always can achieve. And if you write this in terms of its constituents, you know that the material parameters that we have to address are essentially all of these. That means you need to high doping, small ground state manifold. This is the broadening. That means you want to go to crystals rather than glasses to have a homogeneous broadening. And, of course, high purity. That's the key also, very high purity. And low phonon energy host means fluorides rather than oxides wouldn't do, for example, right? So we looked at a lot of materials. We focused on YOLF of its availability now, and we find that there are only two groups that can really grow these crystals with high purity. One was Hans Jensen, was at Cryol, now IC Materials, Marotanelli in Italy. And long story short, I'm just going to show you. By the way, once you plot this thing versus lambda and temperature, notice at some point it goes to changes sign. And this is what we call minimum achievable temperature. For example, this crystal had around, it could only cool to 110 Kelvin. Long story short, this is sort of ytterbium Z-bland results from Los Alamos, and they sort of plateaued in 2005. They couldn't cool below 200 Kelvin. Here is when my group, we started looking at ytterbium YOLF, and here is when we went sort of, that was in published in Nature Photonics. Actually, I gave a talk here right after we got these results. And constantly, we have really cooled more and more. Our recent, last year result is cooling to 87 Kelvin from room temperature. These are all in ytterbium YOLF. And we got a lot of press, namely at Physics Today. All right. So the next step, of course, was, please tell me about time.
5 minutes.
5 minutes? Oh, okay. So the next step was to make a device. And that was an eye-opening experience. I was telling Ralph last night, to me, it seems it's easier to have get a set of data, very nice, legitimate data, publish a Nature paper. But when you want to make a gadget, everything has to work always. And we thought we had figured it out, but anyway, we made, of course, we had a lot of failures in the past 6-7 years just to make such a device, right? Because here is ytterbium YOLF. You couple, first of all, light has to bounce back many, many times without any absorption. It has to be very pure. The mirrors have to be very good. This is like 4th of July. You have a lot of light coming out, fluorescence. Almost 99% of the absorbed light is going into fluorescence. So if you want to cool a load, you have to shield it from all this fluorescence light. Otherwise, it would heat. So we have to have some sort of a thermal link that is very good thermal conductivity, very low absorption, and that you also would reject all the fluorescence, and then you have your cold finger. So we've had a number of, 2 or 3 STTRs, actually phase 2, to work on this. And we have, as I said, why are we doing this? Because they would be the first vibration-free all-solid-state cryocooler. Now, as of a few months ago, we have succeeded. This is sort of, again, artist or my rendition of such a device. It's an astigmatic Harriet cell that bounces back and forth, and we can get nearly 100 passes in this ytterbium YOLF because the absorption as it cools becomes very small. Then you have this thermal link, which has to be textured, multiple kinks, even some, we had to design this thing. And then you have to have these coatings that have low thermal emissivity cooling to cut the thermal load, using silica, these aerogels for to cut the thermal conductivity. So anyway, there was a lot of work that went in there, and this is an example of that ytterbium YOLF connected to sapphire. By the way, I cannot give you all the details, but sapphire actually doesn't work because of the thermal expansion is different than YOLF, and as this thing cools, it cracks. So we had to use other solutions, which some of them I cannot reveal. All right. So I just want to say that we have managed to cool a detector. And so this is the world's first all-solid-state cryocooler. And we have cooled it to 135 Kelvin. And this would be coming up at Clio, an invited talk, and also it will be submitted, actually. It's ready, the manuscript. We have to get approval from the funding agency to Nature Photonics. What we are really working on, I'm not going to go through that much, is with working in collaboration with Jun Yi at NIST to cool these silicon single crystals cavities that he uses as a reference to stabilize these his lasers. And he has the most stable laser in the world. But they go through hell by using this liquid nitrogen because they need no vibrations. And our technology matches that perfectly. So we have a DARPA program to cool, but we have to cool it to 124 Kelvin. So this is our next goal. And anyway, so in the last minute or so, I'm going to talk about radiation balanced laser. Can we use this concept to make lasers that don't generate any heat? In other words, can we balance the cooling that happens from this anti-Stokes fluorescence with the quantum defect? So again, any laser, most lasers, optically pumped, behave this way. You pump it. There is this quantum defect. These things go to heat, and you have laser happening here. And so you say the quantum defect is the difference between these two. These are the photon numbers. And of course, there's part of it also goes to fluorescence. Both of these are positive in lasers usually. That means you pump here, the fluorescence and laser, they're all energies are below what you have the pump. And then usually lasers heat up. You have to do a lot of thermal management and beam degradations, and a lot of things happen. So the thing is now, if I move the pump here, notice, now I am in the anti-Stokes regime. That means, can I balance this cooling, this heating, the quantum defect with anti-Stokes fluorescence? And the answer is yes. And actually, this was proposed by Steve Bowman from NRL shortly after observation of laser cooling. And he even showed it in ytterbium YAG rods. So last year, I got a new MURI that I'm leading that concerns this. It's called MARBLE, Multidisciplinary Approaches to Radiation Balanced Lasers. And so we have been focusing on disk lasers. And I'm going to go through this a bit fast. So we have demonstrated right now, and I'm going to present this also at Clio, the first disk laser, which is radiation balanced. We actually can tune it from cooling to heating. It's a laser that can self-cool, or it can go to heating, depending on all the parameters, the power. And also there is one intra-cavity scheme that we have using VEXELs, vertical external cavity lasers, that you can tune it by either wavelength or power that would go from cooling to heating. So this is very important for high-power scaling operations, right? Because right now the disk lasers are workhorse for high power. Actually, they're competing with these high-power fiber lasers. You can get 4 kilowatts out of a single disk of ytterbium YAG. But again, thermal instabilities and modal instabilities due to temperature gradients limit the amount of power. So if you can scale up these things to high-power lasers, and this is not what I'm going to do, but we're just going to show proof of concepts, it would help those issues. So at the end, I want to acknowledge my group. I call them the cooling group, the senior postdocs, and senior research staff, the graduate students that are working on the cooling project. One of my undergraduates also happens to be here. Where are you, Salim? Here. There you go. And my collaborators, of course, Richard Epstein, Marcus Helen, and Mauro Tonelli from Italy. And these are former PhD students, especially Chad Hoyt, who started this whole thing, cooling, in my lab many, many years ago. And with that, I'm going to end with this picture, which was actually winner of the 2012 photo contest in Optics and Photonics News by my then postdoc, now research scientist, Alex Albrecht, that shows the mixing of these 3 colors. They did this beautiful picture. And with that, I thank you all.
Great, thank
Yes.
On the cooling, it seems that the higher upper threshold you get, the less effective that would be for the laser, because the relative amount going to fluorescence relative.
Oh, there is a delicate balance for each one. Yeah. You know, was.
That you were saying for high power laser operation, it seems like that would be exactly the area where it would be more challenging.
No, at the end, it's. I mean, first of all, the disk laser, the nice thing about them that you just scale them up by scaling the area, right? And so these are right now, of course, we focus to tiny spots. These very high power lasers, they are of like centimeter or more than a few centimeter spot sizes. But aside from that, yeah, that's there is obviously once you tune, there is both the tuning between the pump and these things. So you can really tune your laser, the pump laser, to be very close to your laser and far away. So your anti-stoke cooling is very large, and so you also get very high efficiency. So there is a lot of parameters, but you can scale it up. There shouldn't be an issue there.
There will be no heating. You can still scale up.
Yeah.
Could you kind of get rid of the luminescence away from?
So we'll go on. Next talk is going to be by Enrique Galvez from Colgate University. We'll be talking about interference of one or two photons.
That's right. No, I think it's showing me.
Just click swap displays.
Oh.
If you get the cursor over there, you see it.
Where is the cursor now? Okay.
Kiko, I think you could go back to your control panel that you had up just a second before.
Yeah.
Your control panels. You went to displays and looked at arrangements.
Okay. Displays,
It's arrangement.
arrangement.
Uncheck mirror displays. And then go back. You should get the view that you had there in the slideshow on the big screen.
All right.
Oh. That's the way it's supposed to work anyway.
Now, if my mouse were to move,
Now you have the mouse. So
I have the mouse
if you
here.
close it and reopen it, that worked for Mansoor.
Oh, to close the.
Yeah.
Oh, save. I think we have to mirror this properly. Okay, so I go to invitation, and so I'm going to tell you about some little adventures we've been having at Colgate. Perhaps if we were to see something about being a professor at undergraduate colleges, you don't have to spend all your time writing proposals to get funding for graduate students, so you have time to have fun in the lab, okay? And we've been having some fun in the lab. So let's see, is there a laser pointer somewhere? There was. Okay, we've done this work at Colgate University, is up here in central New York. Of course, right now, it looks like that. Fortunately, I was able to escape the bomb cyclone and be able to be here with you. I'm going to show you some data that was taken by some students. And then Laura Coyle has been an illustrious student here, graduate student here at Arizona. And then here, attending our Logan conference, and Brianna Holmes, that presented posters yesterday. And then I have some collaborators funded by the National Science Foundation. And I'm going to tell you about two experiments. These experiments started out with us talking about, wouldn't it be cool to do this experiment? And we went ahead and tried to do that, and did that. And as you will see, there's a lot of cool thoughts that come when you do these experiments and you find the results that you find. So I'm going to talk about a little bit about interference, just as an introduction, then about the single photons in a delayed choice interferometer. That sounds already very juicy. And then something called the spatial probability amplitude of photons. So, okay, so we need to talk about light, right? So particles said, now who's this person? Who was this person? All right, Isaac Newton, and he proposed a corpuscular theory, which remained viable through the 18th century. And then Wave said, this gentleman? Young. Thomas Young. And he did an experiment on the interference of light going through two slits. And after that, it became clear that light was a wave, and it became widely accepted through the 19th century. Then finally, this gentleman, I don't need to ask, proposed the hypothesis that light consists of quanta, and it explained the photoelectric effect. Okay, so really, if we're going to do an experiment with photons, I need to get a little bit into quantum mechanics. Okay, but we don't want to put any formulas here. It's already past 4:30. So we're going to use Richard Feynman's approach. And now, Richard Feynman was talking about this concept of quantum interference, which he claims is the only mystery of quantum mechanics. As you will see, it's quite mysterious. And so what he said was the following. If an event can occur in two or more indistinguishable ways, then the probability of the outcome is the square of the sum of the amplitudes for each case. So if you have some event, so you add the amplitudes of one way and the other way, and there's a phase, and then that produces some interference. So when you calculate the probability, you could get either 1 or 0 or somewhere in between. And then that, what it is depends on this phase. And then that is the interference. But now if the possibilities are distinguishable, then there's no interference. And the probability is constant. So that's all we need to know. So let's do an experiment with single photons. So here we have an interferometer. This is a particularly, let's say, simple. It's called a Mach-Zehnder interferometer. Beam splitter here, and two mirrors. So the light can take two paths. So in this case, we're saying that the photon has two possibilities. And if there's no distinguishable features about the two arms, then the probability that photon goes from A to B is a superposition of the photon going through both paths. And then you do some algebra, and then you get that. I'll spare you that. I actually moved out of my talk the derivation because, again, the time. And delta is the phase due to the difference in length of the two arms. So when delta is a multiple of 2 pi, then you get the probability of 1 plus 1 divided by 2. And when the difference in path is an odd multiple of pi, then the probability is 0. And will be destructive interference. And if the paths are distinguishable, then the probability is just 1/2. Okay? So now let's do an experiment with single photons. And so we could have a laser, but a laser doesn't work for doing an experiment where we want single photons and only single photons, because a laser has many photons. If you put an attenuator, sure, you're going to have a smaller number of photons going, but they come at random times, so sometimes they come together. So you're not assured that you have one photon at a time. So we're going to use this process called spontaneous parametric downconversion that produces 2 photons out of 1. So you send one laser coming into some crystal. We use blue photons at 4 or 5 nanometers, and then what comes out are 2 photons. But now energy and momentum has to be conserved, so we have the energy of the pump photon is equal to the sum of the energies of the downconverted photons. And then momentum is also conserved. And Okay. So turns out these experiments are now widely popular in undergraduate colleges and universities to do advanced labs. So here we have how we do this experiment. We use a laser pointer, blue laser pointer. It goes to a crystal, one of these parametric down conversion crystals. One bottleneck is that we need detectors, but then Lowell was talking about how the detectors are cheaper and cheaper, and alpha has something to do with making them cheaper for us. And so then how do we do the experiments? We use this process called heralding. So we have two photons, so then one is telling us that the other one is there. Basically, that's what that is. So there we go. So this is a little schematic, right? So one photon goes straight to a detector. The other one goes to the interferometer. Well, we can go to detector B or detector C. And again, so then the ingredients are the photon source, the interferometer, and then detectors with some electronics. So, and then all fits in some optical breadboard. Okay, and we know what is the probability. So we do an experiment, and so then what we have here are counts that are the times when we get photons both in A and in B, which we call the coincidences. Then we scan, well, we want to change the phase, but the way to change the phase is to change the path length. To change the path length, we need to push the mirror. To push the mirror, we need some electronic thing. So we have a piezoelectric that we apply a voltage to that moves the mirror, that changes the length of the arm, that changes the phase. So that's what that is, a voltage. So as we scan the voltage, we get that the number of counts that we, in this case in 2 seconds, the number of coincidences goes from maximum to a minimum. That would be destructive interference, constructive, destructive, and so on. Interference. And well, let me ask you, students, if delta is equal to pi, where does the energy go? Right? So we have the probability of going from here to B. Delta equals pi, then we're down here. Almost very few photons go to B. Where does the energy go? Go to C, of course. Energy has to be conserved. So, yeah, if you figure out the little details of this, the probability of going to C is 1 minus cosine of phi. So we take data on C, and then we get the complement, right? Energy is conserved. But what is interesting about this is that it brings about this quotation from Dirac that the photon then only interferes with itself. So every photon that is going through the interferometer is interfering with itself. Let's keep going. And we published these type of experiments in 2005, 2010 in the American Journal of Physics. But now I was talking about path being distinguishable or not. So how do we manipulate the distinguishability? All right. Well, photons are not monochromatic, so they have a spread of wavelengths. So if you have light that has a spread of wavelengths, then that is equivalent, or this equivalent to a wave packet. So this is a summation of different energies. So in time, that corresponds to a wave packet. So then this is the time, the extent of that wave packet in time. But now, since the light is traveling at the speed of light, then think about this wave packet as being a flash of light that is moving. And broadly speaking, this coherence length is the length of the photon wave packet. And, okay. So, but now something that we know is that we can get this conversion from here through the Fourier transform. So the Fourier transform of the energy is the time, and so on. So if we have a wide bandwidth, we get a short pulse. Or if we have a narrow bandwidth, we have a broad pulse in time. Okay? Maybe you can start to suspect how we're going to make the paths distinguishable. Okay, so we have the interferometer. Now, if the paths are almost the same length, then you could think that the amplitude of going the bottom way, you have this wave packet, and the amplitude going the top way is this wave packet. Those wave packets overlap. So if the difference in length of the two arms is less than the length of the wave packet, then the paths are indistinguishable, so there's interference. But if one arm is longer than the other arm so that the wave packets come at different times, and they can't cancel each other, so there's a wave packet of a single photon. They can't cancel each other, so there should be no interference. But you can also think that we could put a detector, a timing detector, and the detector can decide whether the photon took one path or the other by timing. And that means that the paths are distinguishable time-wise. Okay, so what are we going to do? Well, we do an experiment where we have, one photon goes straight to a detector. There's a filter. The other one goes through the other detector, through the interferometer into a filter. And the filter has a bandwidth of 40 nanometers. Okay, that translates to a coherence length of 16 micrometers. Okay, think about that being the length of one of these guys. But now, in this particular setup for this data, the difference in length of the two arms is 8 micrometers. So it almost, I mean, that's just a crude representation. But the overlap from the two paths is, let's say, significant. And you can see interference. And now we can quantify the interference by something called the visibility. The maximum divided by the minimum, maximum minus the minimum divided by maximum plus the minimum. So in this case, the visibility is quite high, 94%. The visibility of the interference pattern. Okay, so now let's change the length of one of the arms further. Okay, 28 micrometers. So now the overlap is less. Okay, and we get that the visibility is 0.45. Okay, we increase that to 38. Now you can see the overlap is even less, and now the visibility is 0.16. And okay, let's keep going. Again, what I'm doing is I'm changing the length of one of the arms. Okay, but this change is not large enough to produce a misalignment. Okay, so don't worry about misalignments. And so now we make it 81 micrometers. Okay, so there's almost no overlap. So you could say that the two paths are distinguishable, and then there's barely any interference. We get a visibility of 0.007 if we do a fitting of that. Okay, so then here we have the paths being distinguishable because the photon wave packets are distinguishably coming out at distinguishably different times. Okay, so what are we going to do next? Well, we're going to change the bandwidth. So let's put a 1 nanometer filter. Okay? But we're going to put the 1 nanometer filter not here on the photon that goes through the interferometer, but here. Now these photons are correlated and are entangled in energy. And I'll get more into that. So then what happens there, when we change the filter, the bandwidth now becomes 1 nanometer. So the coherence length now is 640 micrometers, and which is now much larger than 81. Okay, and now the overlap from both paths is very close, and and then the interference is recovered. And this is what is called a quantum eraser. We've erased the path information, and so then there's interference. Okay. Now I'm going to do something else, okay, to make it even more provocative. Okay, because here I'm already doing something striking. I'm putting the filter here. But one thing about this is that both photons have to go through the filters, through their respective filters. So then this, and the energies are correlated because they have to sum up to the energy of the pump photon. So this filter affects the coincidences of both. Okay, but now we're going to get even more extreme. What we're going to do is we're going to, instead of putting the filter here, I'm going to let the light go into a fiber that is 20 meters long, and then put the filter. But now the photon that goes through the interferometer goes through its 40 nanometer filter, okay, and then it gets detected, and then we put a 20-meter cable, electrical cable. So it turns out that light travels through glass at about the same speed that an electrical pulse travels in a coaxial cable. So then these two distances and times, let's say, correspond to each other, so that a photon coming here will arrive at some time, and its partner will arrive at the same time with those delays. And so we do the experiment, and we get, again, the eraser again. But, of course, there's something really troubling here. And the choice of filter decides whether a photon acts as a wave or as a particle. You can think of it in those terms. But this choice is done by the idler photon after the single photon is detected or dead. So are we sending a Terminator there to kill Sarah Connor so we don't have John Connor anymore? Well, not so. It would be fun if we could do things in the past, right? But quantum mechanics is fine with this. So because of the following, the photons are in a common entangled state. And how are we doing this time? Okay. And so they're in an entangled state of energy. So here photon 1 in energy plus, photon 2 is energy minus. Let's say the sum of the energies is equal to half of the energy of the pump photon. Actually, half the energy of the pump photon. So then one could be plus, the other one could be minus. The first could be minus, the other one plus, or the two could have the same energy. So whenever I measure one or the other, I'm selecting either a broad range or perhaps a narrow range. So selecting one also selects the other one. So when the signal photon is detected, both particle and wave information are stored in the data. That is, on the photon that goes through interferometer, there already is, all the information is there. But now when the second photon is detected, we decide which information becomes available. Either a wave type picture where we see interference, or a particle picture where there's no interference. And in quantum mechanics, the measurement of each photon can occur at any time. And then this, irrespective of when those measurements are done. So quantum mechanics is fine. It is just us who are thinking about this time games. And okay, so we're getting close to the end. So you were sitting how many? 1 minute. And okay, so I was going to talk about the second experiment, and maybe I don't have time to talk about the second.
Take us
Back in time. Okay. Okay. I'll go to the punchline of that second experiment. How about that? And the punchline of that experiment was this one. There we go. And that is, we're going to talk about interference, but now in 2 dimensions. Okay. So you probably have seen pictures of people have done single photon interference experiments, and you have a camera that shows that. Okay, but what is important, and that's what my whole experiment that I didn't show you shows, is that the probability of the photon hitting the camera covers the entire picture. And of course, here they show that they see interference of single photons. But the main point is that the dots are the pixels, not the photons. Okay? Now, about this other part, okay, I showed you before, right? But there's something that I want to point out, too. So we have the interferences in B and the interferences in C. But they're not from the same photon. They're from different photons. So the photon comes through here, interferes. Part of that wave of interference is coming here and here, but it's detected either in B or in C, not in both, which is also very troubling. But anyway, so that was my, and there's something to think about. Okay, so then what is a photon? Richard Feynman said it was a wavicle. Roy Gleiber said a click when detected. And then quantum optics says it's a quantum excitation of the field. The field is everywhere where the light goes, and then the photon is an excitation of that field. And then we like to think of ghostly waves of probability spread out in space where it cannot be known to be with certainty and then pop into whole, click, and become localized when measured. It's not just photons, all of matter. So anyway, so I'll stop there.
Okay, we're on then. The last speaker of the day. Well, not today. We have a banquet tonight. We have a guest. Today will be speaking there. But for this session, Brett Pearson from Dickinson College is going to also talk about single photon experiments in and out of the classroom.
All right, everything worked wonderful. Thank you for the invitation. Thank you, Kiko, for such a wonderful introduction to the talk that I'm going to give. And so I hopefully will be able to get through ahead of time even so we can get to where we all want to be. I'm going to talk about some single photon experiments mostly that we do in the classroom with our sophomore level students. So this is in a modern physics course setting in the sophomore level sequence. And then I'll also talk about some extensions into senior projects. Oh, and sorry, I'm from Dickinson College, which is in Pennsylvania, which is cold, but not quite as cold as Colgate. I'll start with a set of 5 experiments that we do with our sophomores. This is looking at proving photons exist, looking at single photon interference, and many of the same ideas. I'll talk about it slightly differently than Kiko just did, but I really focus on the experience the students get in that. And then I want to talk about an extension, originally thinking about ghost interference, and I'll talk about what I mean by that, but then realizing that we actually have to think more about partially coherent sources than we realized in that, and get at some ideas of these non-local effects and trying to think about visibility in interference patterns. So as Kiko just said, it's not really clear what a photon is, and we start with the students by talking about this idea of photoelectric detection. And in the quantum picture, light is comprised of photons, and they come into some detector. An electron is ejected from the detector when the photon hits, and if those photons arrive at random times, the detector registers at random times. In a semi-classical picture, the light is actually an electromagnetic wave that comes into the detector. But sometime during that wave, this electron gets ejected at some random time. The quantum aspect is in the atom in the detector that's doing the detection. And since that electron comes out at some random time during the wave, the detector also registers at random times. And the key point here is that the rate of detection can actually look the same for both theories. And so you're left with two potential conclusions. Either light is a wave with a quantum mechanical detector, or light is composed of quantum particles that arrive randomly, which would be the photon picture. Though all this work really builds off of this Hanbury, Brown, and Twist intensity interferometry, where they were looking at correlations in intensities between two detectors. There's applications in stellar interferometry in this. And all of this is trying to get at what can we learn about the light source. And can we talk about these ideas to try to prove that photons actually exist? So the first experiment we have the students do is to try to prove that photons exist. And we have them use a laser, a dimmed down laser. And we send that light into a beam splitter. We have two detectors, B and B prime instead of B and C. But of course, it's the same idea. And we measure correlations between those two detectors. And the question we ask is, can light be in two places at the same time? And if light is an indivisible particle, like a photon, it hits a beam splitter, it can can only go one way or the other, but not both. One way or the other. If light is a wave and it hits the beam splitter, it partially reflects, partially transmits, and you could see coincidences between the detectors. So it seems like we have a way to tell whether light is composed of photons or waves here. Students go into the lab and actually make the measurement. Here's their data. They get about 100,000 counts per second. These are count rates in the two single detectors. And they get coincidence of about 85 per second. So it's small, but it's definitely not zero. And of course, you expect some coincidences, or what we call accidentals, just electrical background or noise, would lead to some. And the question is, are those coincidence count just these accidentals? And can we claim the light must be photons? So the students actually have to go back and rely on a previous experiment they did. So experiment 0, I lied. There's actually 6, but 1 they've already done. And here they've taken 2 radiation sources and 2 radiation monitors, these Geiger tubes, and they're counting these radiation decay events. These detectors send out electrical pulses, and we talk with the students about what it means to be in coincidence. What it means is that you have some portion of these 2 electrical pulses from the 2 detectors that overlap in time. For a pulse width of tau for these outputs, these are in coincidence over any delay 2 tau. It's called the coincidence time or the coincidence window. For 2 random sources of events, these 2 radioactive sources, all the coincidences you see between these 2 detectors should be accidental, assuming there's no correlation between when one of these samples decays and when the other decays. In fact, you only need 1 sample. You're just going to have 2 detectors and do the same experiment. We go through with the students how to actually figure out how many accidentals you think there'll be in these experiments. I won't go into the details. And what you find is that you find the rate of accidentals for a 2-detector measurement goes like 2 times the pulse width of the detector times the individual rates, R1 and R2. You can actually take this to as many n-fold coincidences as you want. The math gets very tedious as you go up in the number of coincidences, and we really only need 2 here. So we go back to that experiment, experiment 1, and we're going to need to define what we're going to call an anti-correlation parameter. There's lots of different notations for these. I'm just going to call it A sub c. So it's defined to be the ratio of some probabilities. It's the probability of measuring a coincidence, that is, counts at B and B prime at the same time, divided by the product of the individual probabilities, B and B prime. We worked through with the students how you can rewrite these in terms of the rates. And what you find is that this can be written as the rate of coincidences divided by 2 times the detector pulse width times the individual rates. Well, that's just the accidental rates in this case. And so if you have random independent sources, all coincidences are accidental, and A should be equal to 1. If you have more coincidences than accidentals, A would be greater than 1. This would be like bunched photons when they're coming out together. And if A is less than 1, you're getting fewer coincidences. And in particular, for a single photon, A should be 0. You should never see the photon appear at B and B prime at the same time. So we go and we take the data the students measured, we plug in the pulse width for the detectors, and we get 1. So for a dimmed down laser, you get just as many coincidences as you expect from accidentals. But the point is, we're definitely not getting 0 here. And so although the detectors clearly go click, like Glauber was saying, we're still left with two possibilities that we cannot distinguish between. Either the laser light is quantum mechanical particles like photons, or it's a classical wave that divides at the beam splitter, and then the quantum detectors fire randomly and independently. This comes about because laser light is a coherent state of quantum mechanical photons. We don't go through the details of this with the students, but we do talk to them that having A sub c less than 1 is actually inconsistent with any classical theories of light. So if we can find A somewhere below 1, we know we're in a regime where a quantum mechanical theory of light must hold. This is where we know we have a sort of photon picture. And so we're aiming to find A as 0, of course, but we haven't found it yet. So we're going to need a new light source. And the light source that we're going to use, this is a spontaneous parametric down conversion. And Kiko just talked to us about how it works, so I won't go through the details. The point I want to emphasize is that these output photons come in correlated pairs, or twins. And so a photon in one arm guarantees you have a twin photon in the other. And in fact, if you were to measure the anti-correlation parameter for these two beams, or these two arms coming out, you'd actually expect a quite high value, because these are extremely correlated sources. And the students go into the lab. Here we've set up two detectors, A and B. They measure the rates. They measure the coincidence rates, plug it into the formula for A, and you get about 400. So you actually have extremely correlated light source here between these two beams. They are quantum mechanically entangled, actually. But each arm is just an individual random stream of photons coming out independently. Still haven't shown that light is photons yet, although I'm using the word throughout. We finally get to that measurement. So this is the third experiment the students do in the course. This is a conditioned 3-detector measurement. Where you saw this with Kiko. We've got detector A, detector B, and B prime. If the photon model is correct, when you detect a single photon here at A, it means its twin has just passed the beam splitter here, and is either going to be or B prime, or maybe both, depending on how this all works. And the key point is we're only going to look for the coincidences between B and B prime when you see a count at A. That results in a dramatic reduction in the number of possible events. So here we're going to look at the 3-detector conditioned anti-correlation parameter. So it's a lot of words. It's the same definition. It's still this ratio of probabilities. But these probabilities now are conditioned on there being a detection at A. So it's the probability of getting B prime when A is already fired. You can go through some relatively simple steps to write this in terms of the rates, where here you can see this is the rate of all three firing at one time, R sub A, B prime. Here's two sets of data the students have taken. This is higher count rates, and this is lower count rates. For both of the count rates, we see that this anti-correlation parameter is definitely less than 1. In fact, for the low count rates, it's 0.006. And so we have an anti-correlation parameter which is much less than 1, almost 0. And so this is definitely non-classical light. So this was first done, or first really shown in 1986, in the so-called Grandier experiment, where they actually proved that the single photon does exist here at either B or B prime, but never both. The light goes one way or the other at the beam splitter. But note that actually we do see some triple coincidences. It's not 0. A is almost 0, but we're actually getting about 1 triple coincidence per second, and we'd expect that to be 0 for single photons. But of course, again, you have some chance that there's some random event in one of the other detectors. You can go through and do some estimates of what those rates should be. Here's an estimate of the accidental rate for the threefold coincidences. You can see it agrees pretty well with what we actually measure. And you can actually get a pretty good estimate of what this A anti-correlation parameter should be for accidentals only. And you can see that it actually goes as a product of the pulse width here times the twin rates. And so you actually can improve your measurement of this anti-correlation parameter by reducing the pulse widths, making those even shorter pulses coming out of the detectors, or simply just turning down your light source, reducing the number of twin events or pairs coming out. So again, this is what is called a heralded single photon source. And you actually do need to keep the light levels relatively low. As you turn up the light levels, you actually have higher and higher chances of getting multi-photon events. We then do single photon interference, as you just saw here. It's the same setup, actually, as Kiko talked about. Here's a Mach-Zehnder interferometer in one arm of the down-converted light. The other arm goes directly to detector A, and we look at the output of the interferometer when detector A triggers, monitoring B and B prime to ensure we always have single photons in there. As you know, of course, we're going to see interference. Here's interference. Here's the prediction for it. And we really stress with the students that the difference between experiment 3 and experiment 4, which is that in the previous experiment, we looked for the photons immediately after a beam splitter. And we saw that they go one way or the other, but never both. In this experiment, we don't look after the beam splitter. We wait until after the second beam splitter when they've been recombined at the output of the interferometer. And now the photons somehow have to go both ways. And you can see that because the interference depends on the relative distance between the two paths. And so this apparent contradiction between going one way or the other or both is really one of those central mysteries of quantum mechanics that we talk about with the students. We go on and we do a quantum eraser, like Kiko said. I'll talk about it briefly. We do it slightly differently. We use the fact that use polarization to distinguish the difference between the two arms. With the students, we actually do a local modification. That is, we're changing things inside this arm as opposed to the other arm, which would be a non-local modification. But we saw that when we don't watch the photons, there is interference. That is, the photon goes both ways through the beam splitter, and we see the interference. If we then rotate wave plates in the arms in order to label the path information, that is, by changing the relative polarizations, we can tell which way the photons must have gone through this interferometer, then the interference pattern looks like this red line here. And there is no interference. It's been lost as we go through. They must take the single path. If we put a polarizer at 45 degrees at the output, we remove our knowledge. This detector no longer knows which one. You have equal probability of going either way. We've erased our knowledge of that, and the interference returns. Here, that's in the purple. And so you get, and as Kiko stressed, this can be done even after it's been recombined in the delayed choice quantum eraser. And so it really is a sort of strange, amazing thing about quantum mechanics in terms of how this works. The students, the sophomore level students, go through calculations, pretty simple calculations, but calculations nonetheless, to see how this works. We talk about the beam splitter operators, about how some input state here goes to a reflected and a transmitted state of the photons where you have these coefficients. We talk about propagation in the interferometer, where you have a phase accumulation as you travel in path, with a couple assumptions here about the basis states. You can predict these probabilities at the output. And here you see, again, the Mach-Zehnder output is simply 1/2 1 minus cosine phi for one of the output ports, 1 plus cosine phi for the other output port, where phi here is a relative path length phase difference between the two. The students do these calculations. Those lines on the previous plot were actually their results, and their calculations overlapped with that. And so to summarize this part of the talk, the results, when we talk about this with the students, really point towards a wave-particle duality. That is, the light behaves either as a wave or a particle, depending on the situation. And the quantum eraser and the interference experiments really bring up these ideas of non-locality and non-reality. The fact that the action of making the measurement instantaneously seems to affect all of space, or the action of making the measurement imparts properties on the system it didn't previously have. So this really is a fundamental shift in the quantum interpretation, that quantum mechanics tells us nothing about the state of the system until it has been measured. And before then, it's a superposition of all the states. As you can imagine, this setup allows for lots of great extensions for senior projects. One of them gets at these ideas right here in terms of an EPR paradox and Bell's theorem. Bell showing that quantum mechanics can't be missing something. There's no local hidden variable theory that's possible. We've had a student go in and do a measurement of a Bell's theorem using this same setup. I want to talk about a slightly different extension we're working on right now. The idea here is to look at what's known as ghost interference or ghost diffraction. It's one of these non-local effects like we saw in the previous talk. We can use spontaneous parametric downconversion to produce these entangled states, this time in terms of position and momentum. So we take the two arms of the interferometer. We send one way and one the other. We put a pair of double slits in one of the arms. But we don't look for the interference behind the double slit. We scan the detector in the other arm of the interferometer where there is no double slit. And what you actually see is in the coincidence counts, you see interference fringes when you're moving this detector, which is not going through the double slits. And that's pretty strange to think about. The interpretation is sort of that the which way information gets mixed up in the entangled state. We're seeing this non-local interference over here when the double slits are actually there. This was back in 95 when this was first done. Turns out you can get the same result using a classical light source. That is, if you have a highly correlated source, this is a Heaney laser, where they've put a mirror on a galvo and they're moving that back and forth, and then a beam splitter. Here you have two beams, highly correlated, because it's really the same beam, of course, in position and momentum. You can actually see the exact same effect, where here they park a detector here, the double slit is here, and then they scan this detector and look at the coincidence counts. And they see the interference actually in the arm where there is no double slit, but a perfectly classical light source for this. So to see the basic effect, the classical correlations are sufficient. It must not require the quantum entanglement. There's been a lot of discussion on the interpretation of this, about how much of this is classical, how much is quantum. There's lots of potential applications, and so we kind of got interested in trying this out with our students. We found out, though, that we're going to have to think a little bit more, because one of the experiments said they saw no interference in looking at a single arm of the down-converted light, which seems strange because the down-converted light is really just a random stream of photons, and so we expect we should see it there. And so we started thinking about, well, what does the source of the down-converted light look like? So if you look, this is a close-up here, is a schematic of what you think of. Here's the BBO crystal where we're generating the down-converted light. Here is the spot size of the pump laser at 405. And the down-converted photons are being generated at random times and in random locations across the pump beam profile. And so you've got lots of different sources of these coming out now in pairs, but they're popping up at different points in that pump beam profile, random positions and at random times. And so this really is an extended source of light here, and you have to think about what interference looks like from a non-point-like source. Each point here of these down-converted photons is going to create its own fringe pattern as it goes through a double slit. Assuming these are independent of each other, these are generated independently, the patterns add incoherently, meaning you add the intensities of the patterns instead of the fields of the patterns. And this leads to an overall washing out of the fringes. Again, you can think about a visibility, looking at the max of the pattern minus the min to look at how well you are able to resolve the fringes. So I want to briefly quantify this. And again, we had a talk this morning that also warmed us up for diffraction here. For plane wave illumination, so this is the standard textbook example. This would be like a point source at infinity. The double slit interference gives you a cosine squared pattern in the far field diffraction pattern, where that cosine squared argument depends on the separation of the two slits. The single slit diffraction pattern gives you this sync squared envelope here, where that sync depends on the width of each of the individual slits. And of course, when you put those together, assuming that you're in this regime where the separations are small and you're a long ways away, the double slit with finite width single slits gives you the product of the sync squared times the cosine squared. This is all for a point source or a plane wave illumination. If we now extend this to think about not having a point source but actually having an extended source, this would be a line source now. So you've got point sources all along this length B here. And if you now consider the regime where the single slit width in the double slit mask goes to 0, and you integrate over the double slit interference size of the source, you get an intensity pattern that looks like 1 plus the sync times the cos here, where the sync depends on both the size of the source and the separation of the double slits. This is a standard derivation here in Hecht. Well, as we just saw, this is 1 plus something times a cosine. This sync is clearly acting like a visibility. It's some product that you put out in front of this cosine. And you can plot this function for various source sizes B. Here's where point source when B is 0, you get high visibility. As you increase B, the visibility comes down. As the source gets bigger, it looks less good. And actually, if you further increase B and you make it out to the second lobe of the sync function, you actually get a phase shift. And you actually have a minimum on center in this case. The sync, I'll just go quickly here because I'm running out of time. The sync visibility factor is actually the same as the diffraction pattern of width B. It's essentially a Fourier transform over the aperture of the source. That's where this is coming from here. The students going to the lab, and Natalie and Ruthie, who actually did the experiments, are here in the audience. We use a Heaney for testing instead of the down-converted light. It's much simpler to use and get more light. We shine that light on a rotating card. We then put an adjustable slit right after the card, and we can adjust the size of our incoherent source. And then we put the double slit here and then scan the detector in the Fourier plane. What should we do, though, when the single slits in that double slit mask are not infinitely narrow? One option is to put the standard sync squared factor out in front. So now this is due to the width of the single slits. When the visibility is high, that prediction looks great with the data. But you can see as the visibility goes down, we deviate a little bit between the prediction and the data just by putting the sync squared out in front. A second option is actually to do the full integral and return to where we started with the co-squared, keep the sync squared in the beginning, and now do the integral over the source size. I won't go through all the details. It's pretty gory in doing that. But one can go back to the beginning and do the full integral again. Here's those same two plots. For high visibility, you see perfect agreement, again, between the data and both of the models. And actually, for the lower visibility, this full integral over the sources actually hits the data much better. So I didn't quite finish early, but here's the end. For the low visibility, it really becomes apparent, actually. So here's two very low visibility curves. You can see that this full integral model actually really fits the data much better than putting the standard sync squared out in front. In fact, it's very apparent at both of these. And so we really got interested in sort of hung up on the visibility as opposed to just thinking about the ghost interference. But hopefully the ghost interference will be coming here the rest of this year. So I'll just conclude. Talked about the hands-on experience with the sophomore level sequence, and then an extension to ghost interference, including mostly a focus on these partially coherent sources. I want to thank colleague David Jackson, who works on these, Natalie and Ruthie, who are here in the audience. And my co-author would be very upset if I didn't take this opportunity to plug. If you're interested in the quantum mechanics and the ultrafast spectroscopy side of things, there should be a new textbook, graduate level textbook, coming out this year about time resolved spectroscopy and experimental perspective that I've written with Tom. So thank you for your attention.
Thanks, Brett.
Thanks.
Questions for Brett?
There's food and